Okay, now I'm going to try to make today the last day of new material.
Cool.
And then we'd have the lab, and then that'll be it. So I'm aiming for no class
How about Monday?
next Wednesday.
Lab.
What?
Oh, Monday is lab.
That's the plan. But I need to get started covering this, if there's to be any hope. Okay, I'll try to keep the same. Since it's not relevant to this class. Okay, now, so we're looking at the boundary value problems, finite difference method, which I covered at the end of last time for the linear case. Okay. So what we have is our boundary value problem is of this form. Y double prime is f of x, y, y prime. And we want to discretize that using these differentiation rules, like in the linear case, to arrive at a system of equations to solve f of y equals 0, which we can solve using the methods I was covering before, like Newton's method or Boyden's method. In fact, in the final project, you'll be using both of those to solve this system. So what I'm going to cover now is, what is the system? Okay. So, all right. So now I'm going to write out, well, first, I'll do that on the next board, but using these approximations. Y double prime of xj is approximately yj plus 1 minus 2yj plus yj minus 1 over h squared, where h is your spacing in delta x. And just to recap from before, your boundary conditions, y of a is alpha, y of b equals beta. Our h is b minus a over n plus 1, where n is chosen, the number of unknowns you're going to have. And your boundary values, y0 is alpha, coming from here, and y capital N plus 1 equals beta, coming from here. So those are specified. So here's our second derivative approximation, and then our first derivative approximation is yj plus 1 minus yj minus 1 over 2h. Y sub j is approximation to the solution y at xj. Xj is equal to a plus j times h. So we have equally spaced points between a and b. All right, so now that my notation is set, I can describe the component functions of capital F here. So my vector y consists of all your y values you're going to solve for, your unknowns, y1, y2, up to y capital N. So, so my function f of y is defined as follows. So for your first component, so you can think of it as approximation of y double prime minus f of x, y, y prime, which you want to be 0. So we're just moving everything onto one side. So our first component function will be, first we use this rule for y double prime. So with j equal to 1. So it's, and also I'm going to multiply everything by h squared to have fewer fractions, because fractions are annoying. So I have y2 minus 2y1 plus y0. So this comes straight from here. But what is y0? Alpha. That's our boundary value. So we'll just go ahead and fill that in. Okay. Then minus h squared, because remember we're multiplying everything by h squared, of f of x1, y1, and then we want y1 prime. But that is y2 minus alpha over 2h. Okay. So this is our approximation of y1 prime. This whole thing is approximation of h squared y1 double prime. So in other words, we're evaluating our boundary value problem at y1. But to represent y1 prime and y1 double prime, we use these rules right here. So this is used for that. Okay. And then we just keep going. So for instance, the second component, f2 of y, this is a vector y here, is equal to y3 minus 2y2 plus y1 minus h squared f of x2 y2, and then y2 prime, which is y3 minus y1 all over 2h. Okay. This should not have a vector symbol. F, each component function of f is just a scalar valued function. Okay. And then down to the second to last component. So we have yn minus 2 yn minus 1 plus yn minus 2 minus h squared f of, x n minus 1, yn minus 1, and then yn minus yn minus 2 over 2h, and this is yn minus 1 prime, just like this is our approximation of y2 prime. And finally, fn, our last component. So we're going to have yn plus 1, which is beta. So our boundary value goes there, minus 2 yn plus yn minus 1, minus h squared. Ooh, that's going to be bad. Xn, yn, and then for our derivative, first derivative, we have beta minus yn minus 1 all over 2h. So this describes the function we want to find a root of. So we have n equations, these n equations, in the n unknowns, y1, y2 up to yn. And once we solve that, we'll have solved our boundary value problem. So any questions about the definition of f?
Is this on our final or how did I get there?
Yes. Yeah, but the two functions fd, fd linear is what I covered at the end of last time. There's fd Newton and fd Broyden. Yeah. So the thing is, once you have this function defined, you can solve this system of equations using any of the methods that we covered before: fixed point iteration, Newton's method, Broyden's method, any of those. So for a final, you only have to use, I think it's just Newton and Broyden. Mm-hmm. Okay. So in order to use either one of those methods, though, what additional information do you need? For Newton's method?
Derivative.
You need a derivative. Now, if we're solving a single equation, that we refer to it as a derivative. When it's a system of equations, we need, what do we call it then?
Inverse matrix. Or Jacobian.
Yeah, we need the Jacobian matrix, which would then be inverted. Okay, So, all right. Now, one thing to keep in mind here, notice that each one of these component functions, like component fj, depends only on yj, yj plus 1, and yj minus 1. Because of that, that means that the Jacobian matrix, most of the entries will be 0. So really you're just going to have diagonal entries because of this. You're going to have super diagonal entries because of yj plus 1, and subdiagonal entries because of yj minus 1. In other words, the Jacobian matrix is going to be tridiagonal. So I'm going to describe the entries on the diagonal, sub, and super diagonals, and then you'll have your Jacobian. Okay. Just out of curiosity, how many of you are most likely going to do the coding project instead of the oral? Okay. All right.
Maybe.
Well, that's more than last time. I think last time only 2 people did it. Okay.
When to do that?
Well, okay. Regardless of what I actually say for a deadline, I have to turn in the grades on May 16th, which is a Monday. So in the morning, 11 a.m. So please give enough time for me to evaluate what you did.
Okay.
So, all right, yeah, because that's the one deadline I cannot extend. All right, so the Jacobian of f. So we have first the diagonal entries. So entry II. Okay, so that is the partial derivative of fi with respect to yi. Okay, so if we're differentiating with respect to yi, we're going to have a minus 2 from the second derivative approximation. And then we have minus h squared df dy, and you'll plug in the same values. Xi, yi over 2h. Okay. All right. And because all the other terms have derivatives of 0. And then, so that's the diagonal. On the row I, column I plus 1, so this is the super diagonal, where rows are less than columns. So that's the partial derivative of fi with respect to yi plus 1. So from your second derivative approximation, you're just going to pick up a 1, and then you're going to have, okay. So what's going to happen next is, you're going to have minus h squared, partial of f with respect to y prime, because you look for where does a y plus 1 appear? Only here. So you plug in xi, yi, and then you have these. However, we are differentiating with respect to yi plus 1. So what do I still need to do? Yeah, I need a factor of 1 over 2h. You're differentiating this with respect to yi plus 1, which produces a 1 over 2h factor. So really, this will simplify. You'll have minus h over 2 times this. Okay. And that's what I have in the notes, but I wanted you to see where it comes from. And finally, Jacobian of f on row I, column I minus 1. So this is the subdiagonal. So that's the partial derivative of fi with respect to yi minus 1. Well, it's going to be almost exactly the same as what happened here. what's going to be different?
There will be a minus 1.
Yeah, I can have a minus 1 over 2h, which will combine with the h squared, or minus h squared, to give you a plus h over 2 of all this. Okay, and that's it. So you fill in the entries of your Jacobian, and then you're able to carry out, for instance, a Newton step. So your step from iterate k to iterate k plus 1 is Jacobian with yk plugged in, inverse times minus f, also with yk plugged in. But keep in mind, of course, you would, like in MATLAB, you could use backslash, for instance, or even my tridiag solve, or whatever code you got when Amber taught that. Solving a system of equations, you're not actually computing the inverse. Although for Broyden's method, for first iteration, you would compute the inverse, and then Broyden's method would modify it after that. And then xk plus 1 is equal to xk plus sk. In the notes, I have sk plus 1 for some reason, which I call it sk because that's consistent with my earlier notation. But the point is, it's a negative against you from one iterate. Oh, actually, I should call this y, not x. That refers to the solution of our boundary value problem. We'll be calling it y. I also want to mention in the notes, when I describe the equations for f, there's a couple typos. I actually left out the letter f in a couple of those. You can see from here where to fill it in, and I'll fix all that stuff shortly. Okay. Now, we talked about what you need for Newton's method. One thing we need, of course, as we discussed, is derivative. Was there a question?
Yeah, what's the difference in doing the subscript like I plus 1 and then I minus 1 instead of doing I plus 1 I?
In here?
Yeah.
None.
Okay.
You just adjust the indices accordingly. I think the only reason I did it this way as a convenience is this way of describing what is on a single row. So these three formulas give you the entire ith row. So it depends on how you want to write the code to set up your matrix. If you want to do it row by row, then this is the best way to go. But
So what happens when that Jacobian when I is 1?
Oh, here?
Yeah.
You would then you wouldn't have that entry because your first entry under subdiagonal would be 2, 1, 3, 2, and so because you have n diagonal entries, and you only have n minus 1 of these.
So we would just set the diagonal for 1 and then start with 2.
Yeah, and then the opposite situation for this, you would start at 1, 2, 1, 3, etc., going up to n minus 1 n. Yeah. Okay. Okay. For Newton's method, besides a derivative, what else do you need? What else does Newton's method require besides, we talked about how it needs a derivative. So we took initial guess. So you need a decent initial guess. And preferably something that's at least chosen somewhat systematically, because if you just try a random initial guess, chances are your iteration is not going to converge. So here's what you can do. What I'm going to recommend is this function. So alpha plus beta minus alpha over b minus a times the vector x minus a. Now, why on earth would I choose this? Because this is the linear function that equals alpha at x equals a and equals beta at x equals b. So in other words, it is the only linear function that satisfies the boundary conditions. Because your solution is required to satisfy boundary conditions. You might as well start with something that satisfies the boundary conditions. That's something pretty simple to come by. So really, you can think of this as doing just straight interpolation, or solving this high school level problem of finding the equation of a line passing through 2 points. These 2 points. Because actually, this is point slope form that you see right here.
Wait, what is point slope form?
This equation.
That.
Using
Y minus y1.
using a alpha as the point. And your slope, your rise over 1, is beta minus alpha over b minus a. So, okay. What?
So it's an alpha on top. Never mind.
Oh, okay. Oh, you thought this was something else?
Yes.
Yeah. Oh, and x, I have a vector x, but that is just a vector of all your equally spaced x values, x1, x2, up to xn. I gave a formula for xi on the previous board. Okay, so now you can set up your initial guess and start Newton's method off and running, and hope it converges. Apparently, in the assignment, though, it does converge pretty quickly if the method is implemented properly. Okay.
So for this to work, do we need to make alpha a vector of all the same values so that we can subtract
Oh,
a as well?
actually, MATLAB is smart enough to figure that out.
Oh, okay.
When you're adding like a scalar, adding it to a vector or matrix, it automatically expands this. Yeah, so it's kind of convenient. Yeah, and if you're not sure, you can make a, alpha times a vector of 1s or something, but you don't need to. Yeah, so it's reasonably friendly that way. Okay. Now, one thing to point out is, the reason why we developed Broyden's method was because Newton's method is so expensive. It's solving a system of equations every step, every iteration. However, that's not so bad here because the Jacobian is tridiagonal. So the work per iteration is order n floating point operations instead of a general n cubed. That would make Newton's method quite impractical. That's knocked down to n squared by Broyden's method. But so that's one thing that's nice, is that the Broyden's for this problem does not give you as much of a advantage, or maybe hardly any advantage at all, on compared to Newton's method. Okay. All right, and I also want to mention that no matter which method you're using, because of these differentiation formulas that we're using, the order of accuracy of your computed solution, order h squared, because the differentiation formulas that we're using for y prime and y double prime are second order accurate. And that's why in the assignment, I have you guys solve the same boundary value problem of 2 different grid sizes, like 100 points and 200 points. And because what you should observe is your error decreasing roughly by a factor of 4, because it's h squared, if you double the number of grid points. What you could do, and this is something that was covered last semester, and it's not part of the assignment, but if you want to try it, you can. Suppose you compute 2 solutions of different grid sizes. You can try performing Richardson extrapolation. So this can be with a Richardson extrapolation, you can, for instance, if you have 2 second order accurate solutions, the you can combine them in a simple way, as was taught last semester with Romberg integration, to get a fourth order accurate solution and so on. But it's kind of a pain because your solutions, like if you use 100 points and 200 points, you have different numbers of points. So you can't add them. Unless you take your solution of fewer grid points and you do some sort of interpolation to fill in the gaps. So that's something that's possible. So. And again, not something I put in the assignment because it is a pain, but I just want to let you know something that could be done. Okay, so any questions about this, especially for the assignment, for setting up Newton's method or avoidance? All right. Now, I want to see how much of this I can cover in the final section. So there's a bonus problem in the final assignment. To solve the boundary value problem, a linear boundary value problem, using Rayleigh-Ritz method. And I'm happy to offer a substantial bonus to anyone who does it. So I'll cover as much of the method as possible, and 45 minutes, so it looks like I can get through it. Then on Monday, we'll be in the lab, looking at code for all of these things. Okay, and that might be helpful for the assignment as well. Okay, so I actually brought up Rayleigh-Ritz method in 606. Here it's using it for a highly specialized problem. Okay. But so this is just for the linear case. So first, one commentary I want to make on the methods that we've seen, like shooting method, finite difference method. We saw a shooting method. That's basically a one-dimensional method. So it's good for these two-point boundary value problems. There's no analog for it in higher dimensions, because boundary value problems, as you're learning in 606, those of you who are in that class, are important in any number of dimensions. You could have a domain of any shape and have solve a PDE in it and impose boundary conditions. But this is hardwired to this one-dimensional case of getting from alpha to beta. Whereas the finite difference method that we've just been talking about, that does generalize so 2D, 3D, etc. But it's best suited to nice domains, like rectangular domains, for instance. So the differentiation formulas you're using are really based on that, and it's easy to take boundary conditions into account. But if you have complicated geometries, finite difference doesn't work so well. All right. So we're going to see now Rayleigh-Ritz. And this is closely related to very well-known approach to solving PDEs, finite element method. Finite element. So this is good for n-dimensional problems on complicated shapes, etc. Now, today I'm just going to look at, back to one dimension, same kind of problem we've been seeing, just so you can more easily compare this approach to the other ones that we've been talking about. It's linear two-point boundary value problems, and Rayleigh-Ritz really is best suited to linear problems, but in whatever dimension or domain you're talking about. are dealing with. Okay, so we'll take a look at a linear boundary value problem, but not the same 2-point problem that we've been dealing with. I'm going to change it up a little bit. So we have minus p of x y prime. So you take y prime, multiply by p of x, and then take a derivative of all of that. So in other words, there's a product rule happening with this outer derivative. Plus another coefficient q of x times y is equal to some right-hand side f of x. So it's non-homogeneous. And x is between 0 and 1. And then we'll impose boundary conditions. Y of 0 and y of 1 are both 0. Okay. Now, those of you 606 people, what kind of problem is this? Dirichlet boundary conditions, but the overall type, like the type of ODE, Sturm-Liouville problem. Yeah. So it's a non-homogeneous Sturm-Liouville problem with homogeneous Dirichlet boundary conditions. Okay, and the rest of you can ignore that. So. Okay. In 417 that would have come up, but I don't. You probably block it out of your mind, right? Yeah. Okay. You will.
There's no way around it.
Yeah. Okay, and I'm going to assume that p of x is positive, and q of x is non-negative. Okay. Now, we could try to solve this problem like using a finite difference approach. That's what I covered on Monday. But we're going to try a very different approach in this case that actually involves integration rather than differentiation. Okay, so the first thing I'm going to do with that ODE is I'm going to multiply both sides by a function called a test function, and then integrate. So again, it's going to give me, I can integrate from 0 to 1. So I have a function u of x, which is called a test function. And then I have derivative of p du dx, okay, plus u q y of x. Oh, sorry, that should be a y. Okay, so y is my solution. I'm getting myself confused with 606, where solution is commonly referred to using the letter u, so I better be careful here. Okay, on the other side we have, something seems odd here sign-wise. Okay. Oh, okay. Sorry. A minus only belongs to this term right here. That still has a plus. Okay. So typo the notes that you can fix. Now, the right side, same thing. Multiply by a test function, u of x. Integrate 0, 1. Now, this operation of multiplying through by some function and then integrating, again, like 606 like language, what was that? What is that? What operation is that?
Inner product.
It's an inner product. Yeah. So So I'm taking inner product of both sides with u of x. Okay. All right. Now I'm going to mess with just this first term right here using integration by parts. All right, so I have minus the integral of u of x dx of p dy dx. Okay. Now, if I do integration by parts where my u is u, so that's convenient, and this is my dv, this is convenient because now it's very easy to get my v. It's just what's inside the differentiation. So now I will have, okay, I still have a minus out front. So I'm going to have u of x, p of x, y prime with limits 0 and 1. And then minus the integral of v du, but I already have a minus, which gives me a plus. And then I have p of x, u prime of x, y prime of x. Okay. All right. Now, question? Okay. Now, let's see. So I'm going to require that these test functions u of x satisfy the boundary conditions. So the u of 0 equals u of 1, 0. So that way I'm basically working with this one vector space consisting of all functions that are continuously differentiable. So it's really working with C1 of 0, 1, which is the vector space of continuously differentiable functions on 0, 1. But not all functions from this space, just the ones that satisfy the boundary conditions. So I'll introduce more notation. C1, and I'll put a subscript of 0. So functions in the previous set, C1 of 0, 1, that are equal to 0 on the boundary. So that's where a subscript of 0 comes from. So it's very common, if you use the space C of a domain, that's all continuous functions. If you put a superscript here as a number, that indicates how many continuous derivatives the functions have. So we only need one in this case because notice, now we only have first derivatives. We don't need, it's a second order differential equation for y, so I think, oh, you need a second derivative, but now we don't anymore.
And since u0 equals u1 equals 0, that goes away, right?
Yeah, that's why I'm doing this. So this is gone. So now I can take this remaining integral and put it back in what I had. So now what I get is called the weak form of my boundary value problem, which is so integral of p of x, u prime, y prime, plus q u y equals integral of u f. Okay.
And that came from.
From this with the integration by parts taken into account. So I just replaced this with that. And then I kept the rest of this.
Oh, the Q X is just in a different place. Okay.
Oh, yeah. Okay. All right. And I want this to hold for all u, test functions u in this space of continuously differentiable functions that vanish on the boundary. So I've changed my differential equation basically to an integral equation. So I could try to find a function y that solves this, and if my function y that I get actually has two continuous derivatives, then it's actually a classical solution of the differential equation, the original equation. But if it only has one continuous derivative, then it's called a weak solution. It can't be classical because the number of required derivatives doesn't exist. But it's still acceptable as a solution in this weak sense. Okay. So the reason we call it weak is that we require fewer derivatives. Okay. Now, okay. Now it turns out, though, that given right assumptions on the coefficients, this weak form and the original form differential equation actually have the same solution that has two continuous derivatives. A way to, it turns out that this equation is satisfied if and only if we can if and only if y is the solution of a minimization problem. So I'm going to describe the minimization problem that y solves. Okay. And it turns out that what I'm going to do here is very closely related to when Amber was covering steepest descent as a segue to a conjugate gradient. We're just applying this idea to a specific kind of problem based on this differential equation. Oh, that was such a nice piece of chalk. Okay. Hopefully there's another piece of one around here. Okay. All right. So y solves the original boundary value problem and a weak form if and only if y minimizes this functional I of u, which is 1/2 p u prime squared plus q u squared plus, or sorry, minus u f. Okay. Now, okay. Let's see. I'm sorry, where?
The first one. Yeah, is that you prime or you?
That is u prime. Okay. Now, strange here. Okay. Now this is closely connected to this functional defined on Rn. P of x, which Amber covered before steepest descent. So this is minimized if ax equals b. And A is a symmetric positive definite matrix, otherwise you can't count it as being a minimizer. Okay.
Neighbors in I U. Why is U prime of x squared?
You'll see.
Okay.
Yeah, this is not meant to be the same as that. In fact, you could think of that as being like a gradient of sorts of this, where u is your variable, a vector value variable. Because think of it this way: suppose I take this. If I were to take the derivative of this with respect to
Oh, yeah, it'll be 2 times all
2 times
that.
p of x.
But then it's what times y prime of x, because that is
Yeah,
the derivative you're taking
yeah,
with respect to y, right?
yeah, and the same thing here.
Right.
So
Because the one had the okay, all right.
yeah. Now, as I go through this, hopefully it'll become clear. Just yeah.
I'll be patient.
Okay. Thank you. Okay. So A corresponds to the differential operator from your the original boundary value column. So minus d dx p du dx plus q of x u, which we can describe as LU, a differential operator. Okay. Also, F corresponds to your vector B here. U of x corresponds to the vector x in this function here. And the inner product, so the dot product, U transpose V, corresponds to the inner product of functions, which is an integral of their product from 0 to 1. Okay. So this is how you relate the two kinds of problems. Okay. Also, A has to be a symmetric positive definite matrix. The operator L, this operator, is self-adjoint. So the adjoint of an operator is like the transpose of a matrix, just on more general vector spaces. And is also positive definite. In other words, its eigenvalues are positive. Okay, just like the eigenvalues of a symmetric positive definite matrix are all strictly positive. Okay. Now, so what I'm going to do is, for the Rayleigh-Ritz method, the idea behind it is to solve this problem of minimizing this. Okay. So, okay. Actually, you can see that L is positive definite because the inner product of U with LU is strictly positive for all functions U that are non-zero. Okay. And in fact, you could see that by going back to this weak form over here. This is the inner product of u with Ly. Now, if I set y equal to u, I have p of x u prime squared plus q u squared. P is positive, q is non-negative. This integral is going to be positive when u is equal to y. That establishes is a positive definite operator. Okay, but now I want to focus on setting up a system of equations to solve this minimization problem. So what I do is I'm going to assume that my solution, y, has a certain form. So it's a linear combination of n functions. These are called trial functions. So I'm trying to find a solution that is of this form. So these are my unknowns. As my trial functions, I'm going to pick them out. The CJs are what I actually need to solve for. And I'm not going to say what these VJs are just yet, but we'll just say that they must be continuously differentiable, and they need to be linearly independent, of course, and they must satisfy the boundary conditions, just like the solution does. Because that way, if these satisfy the boundary conditions, y will automatically satisfy the boundary conditions, because they're linear and homogeneous. Okay, so I substitute this into my functional. I compute I of y, and that's going to give me 1/2 integral of p of x of c j bj prime of x squared plus q of x cj bj of x dx equals, okay, or minus integral of f cj bj of x dx. Okay. And what I do now is I take the gradient of this with respect to my constants. Because you can think of this as some function, big F, of my constants, C1, C2, up to Cn. And I want to find the C's that minimize this. Because that will get this as close as possible to a solution of my boundary value problem. So if I take the partial derivative of this functional with respect to C sub I, so what I'm going to get is, okay, so 1/2 p of x. I need to take a derivative of this with respect to Ci. So I have 2 times this sum to the first power now. And then I differentiate this with respect to Ci. Well, the C's are all independent. So most of these will be 0, except for when j equals I, which gives me phi I prime of x by chain rule. And then over here, I have q of x, and then I differentiate this in respect to ci, which is only going to give me phi.
Should that sum, should that be squared?
I'm differentiating now.
But
Oh, this one. Yes, it should be. Good, because I was looking for another factor of 2. I kind of needed it. Okay, so 2 cube x times this sum, Cj, Pj, and then I take the derivative of this with respect to Ci, and I'll only get phi. Okay, and all the 2's cancel, so that's nice. Gone, gone, gone. And then I have this, so minus integral of f phi. Okay. And I want this to be 0 because I'm trying to find a minimum. So you find a critical point. All the partial derivatives must be equal to 0. So now what I can do is, notice I can, let's see, I can factor a c sub j out of all of this, and I can also pull a summation out of this too. So now I'm going to have this sum, and then I'll have an integral p of x phi I prime phi j prime plus q of x phi j prime, or phi phi j dx, all times cj, so I just pulled that out of the integral, equals f of x phi. Okay.
Dr. Ramos, how did you get that last time, the f of x phi?
Oh, differentiating this with respect to ci, all the terms go away except when j equals I, and the derivative of that will be 1. Yeah.
Okay.
Okay. All right. Now, this whole thing is actually a matrix vector product. You can think of this as, well, the whole part of the square brackets as A, I, J. So the entry of a matrix A. And you can think of this as B sub I. So you have solved a system of linear equations, A, C is equal to B. Okay. So your Rayleigh-Ritz method, what you're doing is you're filling in a matrix. These are the entries of your matrix, or they come from here. These are the entries of your right-hand side. And then these are your unknowns. So you set up your matrix right-hand side, and you just do backslash, and bam, you get everything. Now, except there's one little wrinkle here. These entries of A and B are integrals. And for given P of X or Q of X, you're not necessarily going to know how to evaluate those. Also, you haven't chosen your fees yet. And that's what is dealt with on the last few pages of the notes. More specifics about how you form those entries. So I will give a brief rundown during the time that I have left. At least define the fees and also say a little something about the integrals. Because we're not going to be able to evaluate the integrals exactly. You'll have to do it approximately. Okay. So, I'm going to define each fee as a piecewise linear function called a hat function. And it's called a hat function because it has a shape like this. It's 0, goes up to 1, and then back down, to 0, and it kind of looks like a funny hat. And these are convenient functions to work with because their derivatives are constant. So you can define them piecewise. So each one of these is equal to 0 if x is less than xi minus 1. So you can choose equally spaced point. Or actually, they don't even have to be equally spaced. So you have your interval from 0 to 1. 0 is x naught, 1 is x n plus 1. And we have x1, x2, so forth. So x1 and xn are your points where you're defining your unknowns. Because your solution is 0 on the boundary. You're trying to compute these values in between. And I'm going to let h sub I equal xi plus 1 minus xi. So in other words, we can assume equal spacing if you want, but it's not required. Okay. Now, so for the first part of the interval, this hat function is 0. Then, you have this part that goes from 0 up to 1. Okay, so that's the left part of the hat. Then you want to go back down to 0. So that's 1 over hi xi plus 1 minus x. It is for x between xi and xi plus 1. And then 0 after that. So right here is xi minus 1. Right here is xi. Right here is xi plus 1. So it's only non-zero between those 3 points. Everywhere else is 0. These constants are meant to make sure that at xi is equal to 1. So again, it's just finding the equation of a line between 2 points. So the slope is 1 over the spacing. Okay. Now, what's convenient about this is these are easy to differentiate. So phi prime of x has the same 4 pieces. It's definitely equal to 0 on the first and last piece. On the other pieces, it's equal to 1 over hi minus 1. And then for the other one, it's minus 1 over hi. So if you don't have equal spacing, you might have an extra funny hat, like this and then this. So that could happen. Okay. And these are designed to satisfy the boundary conditions. Okay. So then what you can do is, for your matrix, you can plug these in to your integrals, but now you want to define the integrals in a piecewise fashion, conforming to these pieces. So for instance, the diagonal entries of your matrix, the way they're defined are integral from 0 to 1, p of x, phi prime squared, plus q of x, phi squared, dx. So that's the exact definition. But the way you would, if you fill in what these functions are, oh man.
Yeah.
Great. I have an umbrella, but I don't think it's going to do me any good. So if you integrate from xi minus 1 to xi, so this piece, because you don't need this piece anymore. So you're not integrating over all of 0, 1, because over most of that interval it's 0. So for this piece, you have p of x, and then this is a constant. It's 1 over hi minus 1 squared, which you can pull out of the integral. And then for the other piece, you'd have, actually I'll pull it out of the integral now, 1 over hi squared, integral from xi to xi plus 1 of p of x. And then you have this part right here, which is similar. So here you're taking, well actually, here you have to leave it in the integral because there's an x dependence. So from xi minus 1 to xi, you fill in q of x, and then you have x minus x I minus 1 squared over hi minus 1 plus, that's going to be squared. And then we have minus 1 over hi squared, xi to xi plus 1, q of x, xi plus 1 minus x squared. Okay, so now we have something somewhat more specific. And we have similar definitions, I refer you to the notes, for the off-diagonal entries. Because the nice thing about this, because of the hat functions being 0 most of the time, your matrix A is now tridiagonal. So this is a system of equations that can be solved. Also, it is symmetric. Because notice, in the definition of Aij, if I switch I and j, it's the same thing. Because you have phi I prime, phi j prime, or phi I, phi j. So you only have to compute the diagonal entries, and then the subdiagonal entries, which are also the superdiagonal entries. Okay, and then you have similar integrals for your right-hand side b, where you're integrating an expression like this to the first power times f of x. Okay, now, so what you can do is, and this is worked out in the last couple pages of the notes because I'm almost out of time, you can replace P, Q, and F by piecewise linear in triplets. And then, if you do that, you have only linear functions in your integrals. So then you can evaluate the integrals exactly. Better yet, I've already done this for you. It's in the notes. Where I have all the formulas for these entries broken down into various subformulas, like one for each separate integral that needs to be evaluated. Okay. And I should mention the error in using these piecewise hat functions is order h squared again, just like for finite difference. If you want to use higher order functions instead of linear, you can use cubic splines, for instance, which is way harder to set up. Your error will be order h to the fourth because cubic spline interpolation is much more accurate. Okay, so if you want to do this part of the assignment, you've seen the derivation up to this point. As far as filling in all these integrals, the notes have all the information you need. So for instance, if you have a vector for your solution y, and vectors for p of x, q of x, f of x, in terms of those elements, the integrals have already been evaluated. Basically what you're doing is you're integrating like essentially linear quadratic functions, and so in the notes, the last couple pages, the integrals have been worked out. So if any of you want to try the bonus, be my guest. And we could take some time in, if necessary, in lab on Monday to answer any questions, since I didn't get through absolutely everything here. But I'm hoping that whatever we do in lab will help make things a little more concrete. But at least this way, we don't have to have class next Wednesday. And I'm sure you guys appreciate that.
Yeah.
So,
And would that mean that would open up a slot for the final person?
yes, we could talk about that. So, yeah. Okay.